Uh, okay, let us start. We will continue on the code generation issues on the pipeline architecture. We will talk about some algorithms and aspects of loop unrolling. And then, like in the last Tuesday, we will, after the break, we'll have another in-class assignment based on what we have studied in the pipeline architecture. Right? So please, it will be in class as it was last time. So please, if your friends have not joined, you can inform them to join and participate in that. Sorry, my Teams had crashed. So I'm joining again. Is the slide visible?
Yes, sir.
Okay. So we have looked at the basic pipeline architecture, which you already know. And we have we have been discussing about various hazards. We talked about the structural hazard, which will happen. I'm going back, which will happen if two or more different instructions want to use the same hardware resource. So in the same cycle. So structural hazard basically tells us two things. One is it could be because of the hardware. For example, here we show that one instruction is trying to do the mem stage and another is trying to do the instruction fetch. If they use the same memory port, then we'll have a hazard. Or it can also happen that if we, when later on, when we introduce knobs for managing stalls, uh, naturally the usual order of the uh, different stages for an instruction get changed. So it is possible that in one cycle you are going to schedule two instructions having the same stage, like two instructions are trying to do mem or two instructions are trying to do instruction decode. So those kind of schedules will also not be possible. We'll show examples. So naturally, there could be a structural hazard because of that stalled scheduling also. So that will have to be avoided. The next what we saw, I'll just quickly recap, is the data hazard, which is basically due to data dependency, uh, which can be true or could be anti-dependency, output dependency. And the primary one in that is read after write. So this is the situation of read after write. Here, instruction 1 is writing to a register R2, which instruction I2 is trying to read. Now, since this write of I2 will happen in the write back stage, that is the 5th stage, and read of R2 in I2, second instruction, will happen in the decode stage, which is stage 2, which will be scheduled in our normal pipeline way, which will be scheduled before R2 has been written. We will have a dependency hazard here because we are trying to read the value of R2 before the actual value has been written. So this will have to be taken care of. And the simple solution is the hardware detects the data hazard and stalls till the data is available. And there could be ways to minimize that by adding a specific forwarding logic in the hardware as well. So this is what we have seen, that there is a in the instruction decode stage, there is a hardware to detect the hazard based on what are the values at other registers at this point. You can detect that there is going to be a hazard because the next instruction is trying to read a value which is yet to be written. So based on that, you can take the decision of stalls as is shown here. You are adding R1, R2 and putting it to R3, which will happen in this 5th clock cycle. So the sub instruction, which is using R3 as an input, has to be pushed from cycle 3 to cycle 6 by introducing 3 stalls or knobs. And accordingly, the subsequent instructions, it will have a chain effect. Subsequent instruction will also get pushed out. We can minimize this by doing some forwarding. The idea of the forwarding is that when a value has to be written back to a register, before that write back stage itself, the value will become ready, either in the execution stage, if it is a register type operation. So when I'm doing add R3, R1, R2, the execution stage, the 3rd stage of this instruction itself will have the value of that will be written later in R3 in the ALU. So if we provide a shortcut path from the ALU output to wherever we want to use the R3 as an argument for the subtract, if we put this shortcut, which is the forwarding or bypassing, then we will be able to minimize on the stall that is necessary. Otherwise, we would have required to wait till the write back has happened. So here it is possible that we can actually do this earlier. Similar thing will also happen if we are doing a load. So we are doing a load here from the memory to R4, but after that load will happen after this write back, but we can try to get the value that has been read from the memory, and before writing back, we can actually make it available to sub in terms of R4. And so this forwarding will certainly reduce the amount of stall that you are going to see. And we had seen this example before, that there are 2 loads, then add, then store, again 2 loads, subtract and store. So the basic idea is when you are having a stall, instead of losing that cycle, if you can find some instruction from later on, which does not have a data dependency, and you can pull that instruction earlier, move that instruction earlier and use that cycle to improve on the stalling behavior. So for example, here in the first after the first two instructions, add cannot happen because you are having to stall here. Naturally, store will be even further than that. But if we look at the load of value E, then this has no dependency with the earlier instruction. So we can move this load of E before add. And as we do that, then naturally we have gotten additional cycle here. So the stall will get minimized. Similarly, after add, when we'll have to store, naturally there'll be stall here as well. We will need the, after this value has been written to the array, only then it can be stored. So we can also move the load of F before the store so that we get additional cycles. In this way, we can schedule to minimize the stall. And that's the basic idea. So here is a little bit of detailed workout for this, considering different reordering of instructions, scheduling of instructions. So for compactness, I have just written the stages with a single letter. So F stands for IF, D for ID, and so on. To introduce the stall, we need knobs. And those are written as N. And if we need a knob for a structural hazard, then we have marked it as S. Right? So, so if you look at the left, the green column, this is scheduling with the stall. Right? So you can see that the original schedule, which of this 8 instructions, if the stalling was not to be, or data dependency, data hazard is not to be considered, then it can happen in 12 cycles, one after the other. This is simple to see, but we will have stalls. So let's see if we just follow this order, what will happen. We have the load of B, the load of C. Now the add of RB, RC cannot happen till the value has been loaded in RC, right? So we get 3 stalls here, after which the add instruction will be able to get the value of both the registers RB and RC in the decode stage and then proceed from there. Here I have assumed that they're formally, as it is expected, they will wait till the values to be available in the register file, and then the decode stage will be able to access those registers, read the value, and proceed. So we need 3 cycles, 3 stalls here. So with that, the add instruction will finally do the write back in the cycle 10 here of RA. So the store instruction, which will store RA to A, will have to wait till cycle 11 to get this data decoded, the data of RA decoded. And then it can proceed, and it goes up to cycle 14. Now, as we do this stalls, then next we will have the load for RE, which is fine. Then we'll have load for F. Now you can see that because of this stalling, what's happening is the decode of add, which was supposed to happen in cycle 4, is happening in cycle 7. So by the normal scheduling, if you look at the load of F, the decode was supposed to happen in cycle 7. Right? Now, this decode of add has moved from cycle 3 to cycle 7. So what we need now, that in cycle 7, both add as well as load of RF, both are decoding, but there is only one decode unit. So we cannot do that. So this will lead to a structural hazard, right? So we will also have to do a stall here, which just for understanding, I've marked as a as letter S. Is basically again a knob which delays this by one cycle, and then it becomes hazard free. Then sub has to happen by the same way. Sub has to wait till F is in the write back stage. So it introduces knobs, and then the store of RD will happen after RD has been written back with the stalls. So as you can see that the schedule goes up to 19 cycles. So instead of 12, we are now taking 19 cycles. It is a lot more. So there are two things. So this is just a naive scheduling with stalls, hardware stalls. If we do now, we will look at two things. One is on one side we will look at the effect of forwarding, and on which is on the right, and below we will see the effect of reordering the instructions for scheduling, which the compiler can compute and do. So let us first look at forwarding. So let's say we are using the hardware has forwarding logic. So in add, actually we were waiting till cycle 7 to get the value of RC, which is written back in cycle 6. But since it's a load, the value will actually be available in cycle 5 itself. So instead of having 3 stalls with forwarding, we can manage with 2 stalls. And as soon as it is available in memory, in the next cycle itself, directly from the memory, it can be written, it can be forwarded to the decoder stage for the add to use, and we have a less amount of stall to be done. And that means that the write back for RA for add will happen now in cycle 9. Now, if we look at the store, we will, so in the store also we were doing after the write back, but we can observe that since add has been performed in the ALU in cycle 7, that execute stage of add itself has the value that will eventually be set to RA. So with forwarding, we can reduce to number of stalls here, and we can actually decode that take it to the decode stage of the store of RA in cycle 8 itself. So we have less amount of stalls. Then we come to load of RE, which has no data dependency. But again, as you can see that the memory stage of add has been scheduled in 8. So where normally the memory stage of load of RE was expected. So we'll have a structural hazard. So we'll have to introduce a stall here. Similarly, for the load in the of our RF, and then we go with the subtract with the forwarding. So as soon as the value of RF, the value has been loaded from memory, not yet written back to the register, it is ready and it can be forwarded to the sub instruction, reducing the number of stalls. And finally, the similar forwarding from the sub execute of the sub instruction can be forwarded to the decode of the store instruction for RD. And with that, now we see that with just having forwarding, the same sequence of instructions will execute in 16 cycles instead of 19. So we have been able to reduce 3 cycles here. So that is one way to from the hardware. That is one way to reduce. So once hardware provides that, the compiler can make use of that knowledge. Now, let us come down below to see what is the effect of reordering. So here we have reordered one instruction. The load of RE we have moved above add. I have two reordering actually. Load of RE we have moved above add, and load of RF we have moved above the store of RE. Right. So these two movements, because the basic intuition here is these instructions are independent of the earlier instructions in terms of data. So this can be executed in the cycles that we are losing because of stallings, and the stall should decrease because of that. Now, if you see that the first three instructions have no hazard, add still has not got his data till cycle 6. So it can happen now in cycle 7 as it was happening here. But the amount of stall is less because add is coming into the pipeline one instruction later. So that cycle has been utilized by this load. Right? So you have reduced that. Then we have the load of RF. Then we have the store of RA, which has to wait for the write back of RA. Then we have the subtract, and the subtract again needs much less number of stalls now, because the loads of RE and RF has happened earlier than before. So earlier, finally, RF was getting written back in 11. Now RF is getting written back in 9 itself. So when sub comes in, sub needs to use 2 less stalls here, and then we have the store for this RD. And as we work out, this turns out to be that you can do this in 17 cycles now. So two effects. One is stalling, forwarding helps you in getting the data as soon as it's ready. That reduces the stall, and which the hardware helps us to get. And by reordering, we are also being able to get the benefit of reducing the stall. So in the right bottom corner, we do a mix of both. So we are using forwarding as well as we are reordering the instructions. So if you see here, after the reordered third instruction load of RE, there is nothing different. Then we have add, where because of forwarding, we can reduce one stall. RF has an added stall because of the potential structural hazard that would have happened at this point. Then we have the store of RA, which also is happening earlier, the sub and then store of RD. You need to work out a little bit, but this is using this pipeline diagram, it is pretty easy to do. And now we can see that this reordering with forwarding will be possible to be done in 15 cycles. Right? Now, so the question is, can we do better than this? Does it make sense to move RF load of RF also earlier, because add still has stalls, right? And RF has no dependency. So if we can move that earlier, then possibly we can gain better in terms of the stalling. So I'm going to the next slide. We are in the next slide. The first bunch is the same. This is for reference, the original schedule. And in terms of reordering, what I've done, I have moved RF, loading of RF up above the add, right? Just refer here. Here, RF was getting loaded after add. Now I'm moving it earlier. This schedule was 17 cycles. And if I move it up, then the stall in add reduces by another knob and the propagated effect. And eventually this becomes possible in 14 cycles. Now, if we just on this, if we now use forwarding, the combination of that, you'll be able to work out that for the first 4 instructions, you have, I think, if an add with forwarding, add now does not need any stalling. So there is no stall here. Only the store of RA needs a single stall. There's a stall for the structural hazard and subsequently for the store back of RD. So with this reordering and forwarding, we have a solution in 14 cycles. Now, here again, still we observe that, well, though we have been able to, almost get rid of stalls in add, the store of RA still has a number of stalls because it is happening immediately after add. So can we push some cycles here by noting that sub is independent of data independent of this store. So I can push sub up and above the store. And once we do that, up to add, there is no difference. But then sub happens and the store now has got an additional cycle. So the store of RA, which was having 4 stalls, now has 3 stalls. You work out, but eventually, as it happens, it gets dominated by the write back of, that is storing of RD from the sub result. So which finally keeps it at 16 itself. But if you use forwarding, you can work through this. If you use forwarding, then you actually improve 1 more cycle from 14. So you can do this in 13 cycles. So you can see that once the hardware supports stalling and forwarding, to take care of this, a compiler will use this model to know that, okay, this is the minimum time cycle by which the data would be available, and the compiler can work out the instruction scheduling in that way. It has to preserve the data dependency and has to honor the stalling requirements, and accordingly it can generate a very good schedule. So if you recall from the earlier slide, going to the earlier slide, for an original schedule of 12 cycles, our original hazard-free solution was for 19 cycles. And with forwarding and rescheduling, we have been able to reduce it to 13 cycles, almost close to the original schedule. Right. So that is a basic task for the compiler. Naturally, it is a non-trivial problem, because here I have used a lot of human intelligence, and actually I've doing trial and error by doing different schedules. But the question is, how do you get to this kind of a good schedule in general? So just to see the effect of the scheduling, these are some statistics carried out by people on very big codes like GCC's source code, SPICE simulator source code, and take source code, and you can see the benefits that if you do not use scheduling, then the percentage loads that stall the pipe is 54%, but with scheduling it gets reduced to 31%. For tech, this is a drastic improvement from 65% to 25%. So that's the kind of benefit in the pipeline in the presence of data hazard that we are trying to achieve. So the question naturally, let me stop for a brief file and see if there is any question. Any questions up to this point? I think this workout is pretty straightforward, right?
So the M and W for load word and store word clearly need to be distinguished, right? Because like they won't be fighting for resources when we
No,
are
no.
looking.
No. M and W are different. There are 5 stages. I mean, I'm discussing this based on one pipeline model. Pipeline model is nothing unique. So what I'm discussing is based on MIPS 5-stage pipeline. So there are 5 distinct hardware stages. 1 for instruction fetch, 2 for instruction decode, 3 for execute, 4 for memory, and 5 for write back. So they will never, mem and write back will never conflict.
But two mem for one, like for load word and store word, they can lead to a structural hazard.
Yes. That is the reason in cases where that was happening. So that to avoid that structural hazard, again I had to give a stall. I had to give a knock.
Sir, I guess there was some slide in which, like in one of the stages, it was missed.
It's possible. It's possible. I'll share the slide. You correct. You get
Yeah.
that correct. Yeah.
I was just confused over that.
Yeah. Yes. If you can point out, we can see. I'll just load it. It is quite possible because this is not algorithm generated. This is my, hand computed stuff. Is it? Do you remember whether it's in this slide or the next?
Yes, sir, this one. In
Yeah.
this, the stall and forward part, the instructions store word A to RA and load word F into RF.
Store word A to RA. Ah, right. Here you are seeing, right?
Yes.
Yes. This is. I mean, this is my mistake. So there will have to be another stall. If there is another stall, then this goes here. This is your loading RF. So possibly it will need another cycle. Yeah. Thanks for pointing out. I'll correct this. But it's likely this. I've been doing this tick for a long time. Missed out on this. So, but this is I think we have got the idea of what I'm saying.
Yes,
Right?
sir.
This is a basic idea. So naturally, hand execution will always have errors. Sorry about that. Thanks for pointing out. I'll correct on that. But what we the take back from this workout is that if I can give this stall forward model to my compiler, that the compiler will take as input what are the stages, if stages are balanced, how many cycles, and so on. And whether what all forwarding are there, that is whether you can forward from the execute stage to the instruction decode stage, or maybe in some cases from the execution stage to the execution stage of the next instruction. Maybe even forwarding it to the decode stage to the register equivalent value may be bypassed. Whether you can forward from memory to execute or ID, all these will be fed to as a model to the compiler, which is not difficult, which is easy to see. That these are my available options. Now the basic question is, given that and given a schedule, we can work out the total pipeline diagram. Writing this program is not a problem. The question is, given that for a particular schedule, we are getting how many cycles? Now, how do we choose between the different schedules? And because naturally, as you can see, we'll have to preserve the data dependency. As we reorder the instruction, we cannot violate a data dependency. So that is a basic requirement. And we have a potentially very large number of choices. Right? So let us try to take a look at a basic algorithm for doing this. So now we will discuss a simple algorithm for instruction scheduling. So the target is we would like to reorder the instructions within each basic block. So because right now we are considering only the data hazard. We are not considering the control hazard, or so that we are assuming that the branch complications are not here right now. So within a basic block, in a way, which has to preserve the dependencies between those instructions. I mean, unless we preserve the dependencies, we will not have correctness in the program. And the objective, so this is the constraint part. The objective part or the optimization part is it achieves minimum number of pipeline stalls. We will have to minimize that. So how we go about it? We first construct a DAG to represent the dependencies between instructions. Right? So in the DAG, each instruction will be a vertex. Each instruction in the basic block will be a vertex in that graph. And each dependency between two instructions will put an edge in the directed edge in the graph, which goes from the earlier instruction to the later one, based on the data dependency. Right? So construct a directed acyclic graph, represent the dependencies. So here there are 7 instructions. So in this graph on the right, there are 7 nodes, 1 to 7. Now I have load $1, $0, $0. Now if so $1 is getting loaded here. So let's see where all $1 occurs. $1 occurs in instruction 3, it is being read. And in instruction 6, it is being read. So since what you load in $1 is read in what you load in instruction 1 in $1 is being read in instruction 3. So I add an edge from 1 to 3. Similarly, I add an edge from 1 to 6. So this is the dependency. This has to be preserved, right? Because you cannot cannot read $1 before it has been loaded. Similarly, if we look at instruction 2, it is loading $2, which is read in instruction 3. So we have an edge from 2 to 3. Then in 3, we are computing $3, which is stored in 4. We have an overwrite of $3 in 6, and we stored that in 7. So we have a dependency from 3 to 4, 3 to 6, 3 to 7. In terms of 4, it is storing $3, and 6 is actually overriding $3. Right? So you have a dependency there. So in this way, we can similarly in instruction 5, we have $4 being loaded, which is used in instruction 6. So obviously, you will not have a cycle here because certainly this data dependency can never be a cycle. It will always be a directed acyclic graph. So what is this is the graph representation of the dependencies. And what do we need? We need a linear ordering of the instructions which preserve the dependencies. So that basically is the problem statement for the topological sort. So if we do a topological sort of this DAG, keeping naturally honoring these edge directions, then we will get a linear order, which is a viable order of instructions preserving the dependencies. So let us look into that. So this is now the point is that topological sort is not a unique sort, right? It can have multiple, because for example, I can start with 1. 1 and 2 has no dependency. So in the linear order, 1 and 2 can come in any order. Similarly, as you can see, 1 and 4 can come in any order, 2 and 4. So if we do topologically, then we start with that node which does not have a an incoming edge. So it is possible to start with 1 or with 2. So if we start with 1, we do 1, 2, remove them. We have 3, possibility of 3 and 5 to proceed with, and so on. In fact, at the beginning itself, I can start with 5. So there are different topological sorting order that are available that will be possible on the given DAG. So as you can guess that this number of possible, so each one of them is a viable instruction schedule, and we'll have to find the value of our objective function based on which of these minimize that. And as expected, this problem is also NP complete. So not expected to have a polynomial type solution. So again, like every time, we'll fall back on some static scheduling heuristics and try to get a solution which is not provably the best, but usually would be good. So first, that heuristics is, so each time we emit the next instruction, whenever there are choices, like I'm going back. At the beginning, there is a choice between 1, 2, and 5, right? 3 of them. So whenever there is choices, we'll apply this heuristics. First, it does not conflict with previous emitted instruction. Right? We'll have to try to avoid that conflict. Is most likely to conflict if first of a pair. That is, prefer load to add. You know, load and add is a pair. You load and then you add. Right? So we will try to do the loads when there are choice between load and add. And is as far away as possible along the paths in the DAG from an instruction which can validly be scheduled last. Right? So you are trying to, doing things earlier. So these 3 heuristics will drive our algorithm. So the first would be to construct the scheduling DAG, which can be done in order n squared time by scanning backwards through the basic block and adding edges as dependencies arise. So this is but this is one time just to form the DAG. Then initialize the candidate list to maintain the minimal elements of the DAG. And when the candidate list, that is for making the choice with the heuristic. So at any point of time, if there is only one instruction which is valid to be scheduled according to the dependency, there is nothing to do. But usually there will be a few. So that forms the candidate list. So we will have to work on that candidate list. So when the candidate list is not empty, if possible, emit a candidate instruction satisfying all 3 of the static scheduling heuristics. If no instruction satisfies all the heuristics, then either emit a NOP. I mean, let's keep to that. Let's just keep to, let's not go into Spark again. But so on MIPS, emit a NOP. Right? If these heuristics are not satisfied, then you'll have to stall emit a NOP. And remove the instruction from the DAG and insert the newly minimal element into the candidate list. So this has been done. So you go to the next. So let us try to work this out. This was the original sequence of instructions and the DAG. This is the total possible number of schedules. So initially we start. Now initially there are 3 candidates, 1 to 5, because they have no dependency. Of that we can see easily that the load satisfies all the condition. It does not conflict. It is first of a pair, and it is farthest. Certainly 7, which is a sync node, which has only dependencies coming in, is certainly the last will be the last node to be scheduled. Okay, so if we see from 5, it has a distance 2. Actually, there's it is in terms of distance, all are same. So basically, that third criteria is not having any effect. So based on the first 2, this is eligible to be allocated on the schedule. Okay? So we have got the first one. So we'll remove this, and we'll remove the node 1 from the DAG. So node 1 is removed. So now my candidate list is 2 and 5. Actually, I should have replicated the instructions here. Go back. 5 is also a load of 2 is also a load. So between 2 and 5, again, I could have done either of that. We do 2. Now, as we do 2, this is removed, and as 2 gets removed, 3 now becomes eligible for the set because it has no more dependencies. This has already been the dependencies has already been scheduled. Right. So now my candidate list becomes 3 and 5, because 3 has no incoming edge anymore. So it is 3 and 5 is what we get. So basically we proceed in this way, applying the heuristics every time. You can later on, you can work this out easily. So when we end, this is the order that we have finally got in the schedule. So this is the original schedule. So what does the original schedule have? You have load of $1, $2, and you are adding them into $3. So naturally you will need a stall here. This red bar means stall. Then you have store. Then you have load. You will again need a stall here. Now, if you do the schedule in this reordered form, what you have done is, again, the kind of heuristics that we were doing is load here is available. So it can go up and fill this stall slot to delay the add instruction. So that is eventually this algorithm has done. So it has brought load earlier than add, and here is what you have. Then 3, 4, this is the only move that has happened, and now you have a stall free. Of course, this is this is not taking all possible hazards into consideration, but this shows the way the algorithm can actually get a read of the data hazard with minimal number of stalls to give you a workable schedule. Any questions? I think this is as easy as
Sir, suppose one day Intel decides to optimize their processors and thereafter they have a better rescheduling algorithm, and so some knobs become unnecessary. So does that mean we need to change all compilers subsequently?
Absolutely. Absolutely. If you see, the optimization can happen in 2 ways. One is the optimization based on the model itself. and one is optimization based on the hardware implementation. They can optimize on the hardware implementation. That is certainly, I mean, their forwarding logic could become faster and so on. But if they break, what was assumed in the compiler, then certainly the compiled code will not work. It is possible that they can add more. For example, suppose they add more logic so that you have multiple decoding units. Let's say, if you have multiple decoding units, then the kind of structural hazards for which we are putting knobs are no more necessary. So what will happen? A compiler which was written earlier will still, its code will still work, but it will not be able to exploit that added hardware benefit unless it is retargeted again. The other side is, if you look at, if you must have you're doing the architecture course, so you would be familiar with the concept of ISA, right? Instruction set architecture. You have studied that, right? Yes or no?
Yes, sir.
Yes. So instruction set architecture is basically, I mean, the same thing, different communities refer as different ways. So instruction set architecture is basically one of the intermediate representations, as you can talk of, which says that this is the instruction set which has to be supported. Now, how do you do microprogramming for that based on your hardware units is the vendor's choice. And the instruction set, there are a number of instruction set architectures. And it is unlikely that we'll have new instruction set architectures in a short future. So the compilers are working based on the instruction set architecture. If you change that, then naturally you will have to make a lot of changes. But this pipeline stage details and stalls and forwarding, all these of the processor model is getting built into the compiler. So if you enhance on that, it is okay correctness wise, but the older compiler will not be able to exploit that benefit that you have given, which is obvious, because you have now come very close to the hardware. So if you make any changes there, how do you expect? At some point the abstraction has to end, and the realization has to. This is the point where you're finally jumping from, going from the abstraction to the actual realization. You are talking about actual cycles, right? So if you change that, naturally your compiler strategies will have to change. But most of these, and with the hardware stall, it will ensure that even if you have made some changes, your compiler may not generate a code which is as good as it could have been, but correctness usually will be possible, because after everything you have a hardware stall in the processor which will make sure that you are not conflicting, as long as your data dependency is preserved by your compiler. Okay, does that answer?
Yes, sir.
Okay, so let's go back. Continue here. So this was the primary type of data hazard. The other two we have talked of, which are basically renaming. I'll skip. Now, the next type is what is the control hazard? A control hazard is a bigger problem in a sense that the basic hazard is, suppose you have these instructions. Consider the first three instructions. You have branch on equality of R1, R2, which can jump to L. Now, by the time this will be executed, this will be the third stage, right? Branch decision is in the third stage, as we have seen. So by that time, the next instruction add will be in the decode stage, and sub will be in the fetch stage. Now, if this branch is, if this condition is true, the branch is taken, then your next instruction logically is actually this instruction L. not these two. But these are already loaded in the pipeline. So here, what you'll necessarily have to do is first you'll have to stall, because you cannot, I mean, since the branch decision is being made, after instruction decode, you cannot proceed in the add. Or after instruction fetch, when this decision is being made, you cannot proceed. And so you first stall with the knob. Now, once the decision is made, if the branch is not taken, then you will proceed with the add, because that is already loaded. So that's not a problem. But if the branch is taken, then not only the knobs, you will actually have to take these instructions out of the pipe. So you have to flush the pipe. You have to remove these instructions and put the logically next instruction here, which is the OR instruction. Right. So this is the basic control hazard that has to be taken care of. Naturally, again, the concept of forwarding bypassing is also provided for the branches in many MIPS processor. So what you do is instead of doing the branch calculation and decision in the execute stage, you pull it to the decode stage. So that decision will happen one cycle earlier. So the actual branching will happen during execution. That is the reloading and all that. But the decision about calculating the branch condition, because branch conditions are usually very simple calculations, usually just a comparator, right? So it's a simple logic, and based on that, the branch decision can be pulled to the instruction decode phase, which will allow you to do forwarding. Now, if you do forwarding, then you are making the decision now here instead of the EX. You are making the decision in the ID stage of the BEQ. So the next instruction, which is add, will have to stall, but the decision will be known by the cycle 3, before the cycle 3. Okay? So when this decision is being made, the next instruction sub is not been loaded yet. It has not been fetched yet. So when so you can see that if the branch is taken, then again add will have to be flushed, but it needs less amount of flushing to be done. So that is the advantage you get by forwarding this. So naturally flushing and your stalling and flushing is the first option. You can minimize that using forwarding. Another concept which is very, very useful and to be potentially used by the compilers heavily is a notion of delay slot. Delay slot says that basically comes in the specification of the instruction set architecture, ISA, that any instruction after the branch or jump will always be executed. Right? You are trying to make a little bit of a non-sequential model of the instruction set. So otherwise, what we think that if we have a branch, a jump, then depending on that, if there is not a fall through, then depending on that, the jump will immediately happen. And if the jump happens, then the next instruction is not executed. So the delay slot is a deviation from that. So suppose I have one branch delay slot, which is what MIPS has. So which means that whether a branch is taken or not, the instruction immediately following the branch will always be executed. Okay? So it means that you have to schedule instructions keeping this in mind. And if you cannot do that, you have to at least fill it up with a knob. So which means that if you if you are doing the branch here, if the branch is taken, next instruction is still executed. If the branch is not taken, next instruction is still executed. So add will be executed in any case. Right? And you can make use of this information, make use of this feature to schedule some independent instructions here to utilize the stalling effect. So that was the next delay slot. So we have talked about stall and flush, forwarding, delay slot. But what the compilers often do more is speculative execution. That is, since branch is something which hurts you a lot, because you are flushing the pipeline, it takes a lot more of time, lot of instructions lost and so on. But at the same time, the branch often is the most repetitive instruction in a loop. Right? In the loop, you have a body which is linear, and then you have a branch. This is loop is just these two, right? Now the linear part deals with the data hazards, right? So that we have already taken care of. For the branch, we can try to do some prediction based on the previous information. We can make prediction based on the last branching. So you say that if take branch if the last branch was taken, or do not take branch if it was not taken, right? So you'll say that how good is that? Well, it's not bad, because for example, if you consider a loop, this is a very simple logic. But if you consider a loop, then what happens? You come in, you check, and you get into the loop body, right? Then every time you repeat, you iterate, you check, and you get into the loop body. So if you say that getting into the loop body is branch taken, then a typical loop will have branch taken, and ending with a not taken. Right? So if you predict from the fact that the earlier one is taken, if you predict that it is taken, then very rarely you will go wrong. Right? So you organize a code assuming that it is taken. Now, what will happen if it is not taken? If it is not taken, you fall back on that stall and flush, but that will happen far less frequently. But there can be more ways of prediction also. We will talk more about that, but I want you to actually do that assignment. So we'll continue on the rest in the next class. Up to this point, is there any question? No, good. So let me share with you the assignment, very small one, just a scheduling problem, just to practice on what we have discussed. You can take your break and continue on that problem. So this is yeah.
So one small announcement, I'm sending you all an email. So the evaluation of assignment 4 in laboratory and the class test 2 is done. So I also uploaded the solutions of class test 2 in the website. So after the class, please have a look. If you have any confusion or question, I will also mail you one Google form link after the class that you can see. And if you have any confusion, then you can fill it up. Okay. Okay, that's it.
Okay, thank you, Pralay. So this is the assignment, a very simple one. So we have 1, 2, 3, 4, 5, 6, 7 instructions. And for simplicity, I've just written it in a simple notation, because here the exact assembly notation does not really matter. So you have 2 loads, then 2 arithmetic operations, then another load, another arithmetic operation, and the store. So assuming a MIPS 5-stage pipeline, you'll have to schedule with stall to avoid hazards. That's the first part. And the second part is, which should be easy to do. But do it for this particular pipeline as we have discussed. The second would be to construct the dependency preservation DAG as we see and schedule with minimizing stalls as much as you can do. Like last time, you can write your solution on notepad or paper and mail me by 9:55. Last time, a lot of people have mailed even after the class. Unfortunately, that I cannot take because certainly after the class, the whole purpose of the assignment is lost. Okay? So please mail me within this time.
Excuse me, sir.
Yes.
Sir, after the class, mean like if somebody has submitted 9:56, then also it won't be accepted.
No. Up to the point when we decide, I suggested 9:55 because you will always come back and say that I was doing it at 9:59:99 and I had a network problem. So I said, do it 5 minutes before. In class means till we say goodbye from the class, it is accepted. I'll also allow maybe 10 minutes after that because, but quite naturally, if somebody sends it, people have sent it after 1 hour. People have sent it in the evening. Certainly, there is no sanctity of those assignments. Then those who have really done it within the class, their credit is getting diluted if I start accepting in-class assignments anytime in the day. Right? That is the idea. It's not to put you in any hardship. Well, 10 minutes after the class, 15 minutes after, till that is fine. But it cannot be an arbitrary time after the class. Does it make it clear?
Yes, sir. Yes, sir. Yes, sir. Yes.
That's fair, right? That you agree.
Yes.
Somebody wrote to me that he was traveling in train and therefore could not do it. I mean, that's certainly that person's problem. We can't help that. It's a scheduled class. If he's traveling in train, he has to travel. Right? Okay, please go ahead. So,
excuse me, sir.
yes.
Sir, could you please show that slide again, which listed the heuristics once? So for the dependency preservation DAG.
Absolutely. Actually, this one, right?
Yes, sir.
Why don't you take a screenshot, whoever, if you
All
want.
right.
Yeah, why
Yes.
don't you just take a screenshot and keep?
Yes, thank you, sir.
Because I have to keep the assignment in front because.
Yes, sir, it's done. It's done. Thank you, sir.
I think this is the only key information. Otherwise, DAG and traversal and all, there is nothing.
Yes, sir, that's standard.
That's standard. That's absolutely standard. Okay.
Yeah, thank you, sir.
Okay. Welcome. Okay. Proceed.